Internal Routing Protocols Part 3, OSPF Technical Overview and Key Concepts. Now, in all of the nuggets in this series up till now, we've really focused in on a lot of the configuration and showing configuration examples, seeing how things work on live routers. And that's the way I really intend this entire series to be in all the following nuggets. However, this one will be a little bit different. The reason why is we've turned the corner and begun to focus on OSPF. OSPF is undoubtedly the most important concept on the CCIE labs, not just because of OSPF itself and all the nuances that it has and all the, different configurations that you can do with it, but just the fact that it is the underlying glue that binds your entire lab together. If OSPF is not working correctly on your CCIE lab and it falls apart, you're not only going to lose the points for OSPF, but you'll lose the points for all of the other pieces that rely on that routing infrastructure being in place, because they won't work either. So that's why I want to take some special time and really focus in on a conceptual nugget on OSPF. We're not going to see too much configuration in this nugget. However, we are going to take a look at a lot of the key concepts. And in all of the upcoming nuggets on OSPF, we're going to focus solely on the configuration. So here's what we're going to look at. Why does this protocol that was developed in 1987 and officially published in 1989, why does this protocol rule the corporate world? Why is this still the most popular routing protocol out there? Number two, we're going to spend time looking at how OSPF communicates between all of the router and all the OSPF network types, and what it looks like when neighbor relationships begin to form between these OSPF routers, and different types of neighbor relationships, and how to troubleshoot neighbor relationships. There's so much to this. And then we're going to finish it up by going through all of the router types, the OSPF areas, and different link state advertisements, or LSA types, that we're going to encounter with OSPF. Yes, OSPF did come out in 1989, but it's been reshaped and reformed over the years to meet the demanding standards of our networks nowadays. And because of that, we're seeing a ton of areas, a ton of LSA types, a ton of different router types that were never even dreamed of in the original design of OSPF. So we're going to take a look at how all of these pieces fit together. The first thing that we have to look at is, why is OSPF so popular? Why is it the most popular protocol in use in the industries today? Well, first off, when it came out in 1989, the only alternatives were really RIP, and IGRP had just begun to come out. And this protocol blew those away on convergence time. It's very quick to converge and very quick to fix problems on the network. It is classless. It supports variable length subnet masking, supernetting, subnetting, all of the nettings that you can throw at OSPF. It can handle, and it can scale to an extremely large network. With RIP, we had that hop count limit of 16. Now we can go virtually a limitless boundary in any direction. Now, eventually you will reach a scalability limit, but as of yet, we have yet to encounter a network that big. It does support stub capabilities, and we'll look at that when we see the type of areas, so that you can designate certain groups of routers to receive less information so that their routing table can be smaller, and thus the routing can happen more efficiently. It does support authentication, MD5 and plain clear text to validate whatever router you're working with. So if they support clear text, this will support clear text. If they support MD5, which is more secure, this supports MD5. Efficiency. It is very efficient. It does not send the entire routing table with its updates. It only sends hello messages, which are essentially little ping messages here and there to make sure that its neighbors are online. The awesome one that I love, and I just love working with it, is route tagging capabilities. If you haven't seen these before, brace yourself. When we start getting into the advanced OSPF, we're going to take a look at a lot of the route tagging capabilities of OSPF, and this is what it is. Essentially, you can pull out your box of crayons and color routes with different shades. And then when you get to other routers, you can say, well, I only want the blue shades here, and I don't want the red shades over here. So you can filter out different shades of routing entries based on the color that you've scribbled on them with the route tags. And then I know it's kind of funny, but I say the coolness factor, in all seriousness, OSPF is a cool protocol. I have seen people implement it just because it's cool. It's one of the protocols that people look at and they go, wow, you know OSPF? It's kind of like Linux. It's a cool operating system. People look at you if you know Linux and they think, wow, you're not a Windows user. You know how to use Linux. This is the same way. So when you compare it to EIGRP, why does it stand out? Well, EIGRP only works on Cisco routers, and that is OSPF's huge one-up, is the fact that it will work on any industry-compliant router that's out there. Even Windows 2000 now supports OSPF routing, so it can work in just about any environment that you throw at it. When comparing OSPF to EIGRP, EIGRP does win. It is a faster, more efficient routing protocol. However, because of OSPF's industry standardness, it is able to take the cake when it comes to businesses and how they work together. So let's say that you have two Cisco routers and you pull them out of the box and enable OSPF on them. What happens? Well, those Cisco routers are going to start sending OSPF hello packets to the multicast address 224.0.0.5. Now that multicast address stands for all OSPF routers. Everybody will receive it. And we haven't talked about it yet, but we will. The multicast address 224.0.0.6 is used for just the OSPF designated router and backup designated router. But in this case, you can think of the hello as an SOS beacon. It's sending out a hello saying, hello, is anybody out there? Anybody running OSPF? Now, if there is an OSPF neighbor out there, it's going to receive that packet and evaluate it. Now, this is a little bit different when you compare it to other routing protocols. Other routing protocols like RIP and even EIGRP will get the hello packet and say, oh, it's a hello, I must have a neighbor. Not OSPF. It's a little more stuck up than that. You can think of it as kind of a person that really closely evaluates its friends and only finds a friendship in people that it finds exactly like itself. In the same sense here, it's going to go through an evaluation process, and based on all of the things it finds in that hello packet, because it does list a lot of criteria, it may or may not form that neighbor relationship. But let's say the hello packet passes the test, and it says, okay, you are worthy enough to be my OSPF neighbor. Well, at that point, it will exchange its link state database. This is known as a DBD packet, a database description. This is like the cliff notes of the entire roadmap that OSPF has, that OSPF router has of the network. Remember, this is a link state routing protocol. Link state routing protocols don't just have a routing table. They have a topology table where they have an entire roadmap showing them exactly what the network looks like. They will exchange that roadmap with their neighbor. That's a database description packet. From there, all of that new information that the neighbor receives will be recorded in the database, and it will say, okay, well, let me get all that information into my roadmap, and then it will flood it to all of its neighbors. So it's passing this rumor on of all of this roadmap that all the routers need. Once all of the neighbors in this entire OSPF area have exchanged their information, they will have a complete database of what that area looks like, and the SPF algorithm, that's this one right here, the shortest path first algorithm will run. That's where you'll see your processor utilization spike up a little bit on your router, because it's going to put itself at the root of a roadmap. Well, think of it this way. If you were, let's say you were going to go to Disneyland, that was your destination. Would you figure out the best way to get to Disneyland from your parents' house or your brother or sister's house or your neighbor's house? No. You would look at your house and you would say, I am what's called the root. I am the initial source of where I'm coming from, and I will find the most efficient way to get to Disneyland from my house. That's exactly what every single OSPF router will do. It will put itself at the root of that map and find the most efficient way to get everywhere in the network. What does this mean to you? Well, it means that every single OSPF router in an area will have the same roadmap. Everybody has that same topology database, but every router will also have its own unique routing table. No two routers in an area will have exactly the same routing table because no two routers are considered the same root of the network. So once that SPF algorithm runs and they calculate all the most efficient ways to get to every part of the network, all of the valid routes, and you see I put valid in blue, valid routes enter the routing table. Because it may see a lot of different ways to get to a location, but maybe some of them are under construction, or some of them pass through areas that it doesn't know fully how to get to. Some of them might not have a valid next hop address. There's a lot of criteria that could disqualify a route from the routing table, even though it's still in the topology database. Those valid routes, only the valid routes that it knows how to get to, will end up in the routing table and be able to be verified using the show IP route command. One of the most challenging things to troubleshoot during that whole process of OSPF routers forming neighbor relationships is the fact that they're not forming neighbor relationships. The handiest troubleshooting command you'll have for OSPF, and we'll use this a ton, is show IP OSPF neighbors. When you do that command, you may notice some neighbors not showing up at all, or some neighbors that are stuck in the init status, or some of them that seem to be stuck in one or more of the statuses that they shouldn't be stuck in, and we'll look at all those statuses in just a moment. The reason why most of the time is because something is mismatched in a hello packet. Every single hello packet that your router will send out contains all of these 9 fields. It will tell the router's ID, and this is a unique identification for OSPF. It will have the area ID of the router, what area it belongs in. It will have the address of the originating interface. What interface is originating those packets for the OSPF router? The authentication information, if you are password protecting your OSPF domain, will be included in that hello packet. The hello and the dead interval, how often hello messages are sent and how long until a router is considered dead after not receiving hello, will be listed. The priority of the router, that's its information that it uses to elect the designated and the backup designated router for OSPF. And we'll take a look at what those routers are in just a moment. It will contain the designated router and the backup designated router IDs, as in the specific identification address it's using for OSPF, and all of the neighbors that it knows about will be listed in a hello packet. So when it sends a hello to a neighbor, it's going to say, hello, I am a router, and these are the people I know about right now. Now I put a little green X to the fields that must absolutely match in order for OSPF to form a neighbor relationship. It is the area ID, the authentication information, and that just makes sense. And this is the one that gets tough, the hello and the dead interval. The reason this one is so difficult is because that hello and dead interval can change based on the type of network that OSPF is running on. And we're going to take a look at that more later, but tweaking those hello and dead intervals to match becomes a mandatory thing if you want OSPF to work correctly. There's an old Robert Frost poem that has the line, "Good fences make good neighbors." Well, I propose to change that. Just like OSPF has been ratified, I say that Robert Frost poem should now become, "Good networks make good neighbors," especially when dealing with OSPF. And it really supports 4 major types of networks that encompasses nearly everything that we can throw at it in our networks nowadays. And I'd like to start off with the broadcast network type that we see right here. On a broadcast network, and it could be anything, but we'll go ahead and say it is an Ethernet segment. And let's say we have 5 OSPF neighbors here, and this one connects off to some other network down here and so on. So we have these OSPF neighbors that all form a relationship on a broadcast network. Well, when OSPF is configured correctly, this will elect a DR and a BDR for every network segment that has a broadcast capability. Now this DR and BDR are essentially the king and the queen of the OSPF network. Here's the idea. Our OSPF routers typically form neighbor relationships between each other, and this poses a problem when we come to a broadcast-based network segment, because take just this router right here. It would have to form a full neighbor relationship with this router, with this router, with this router, with this router. And every router that we add to that network segment, it is a full mesh style, so it increases the number of neighbor relationships that it has to form. So instead of a full mesh neighbor relationship, which gets really efficient for hello messages, really inefficient for updates, we just form neighbor relationships with just the DR and the BDR. So every router on that broadcast segment has a point of contact that it can communicate with. What do the DR and BDR do? Well, they're the single point of contact to update all of the network information. The BDR essentially doesn't do anything until the DR goes offline. But the DR is going to keep that topology database up to date. So say this router right here is connected to a network segment and it goes down. Well, it's going to send an update to the DR, and the DR will update all of the other routers on that segment. It maintains that sole copy of the database. So that's what the DR and BDR really do and play a role in that broadcast network. Now, in a point-to-point network, we have two routers, typically on a serial connection or some sort of point-to-point connection. Would it make sense to have a DR and a BDR in that case? No, it wouldn't, because there's only two routers on that segment. So in this case, there is no DR and BDR election. All updates are sent to that all routers address. It's actually, I did this wrong, 224.0.0.5. All routers. And this one, the DR and BDR responded 224.0.0.6. This is where that .6 address comes into play. So they can be communicated with directly without disturbing all of the other routers on that network. Now we come to the weird one, the non-broadcast multi-access network. An NBMA network encompasses any network type that doesn't allow broadcast or multicast. That's non-broadcast multi-access. So you might take like a frame relay cloud or an ATM cloud where you have a router attached. Maybe we've got a hub and spoke style topology, and this router has virtual circuits defined to each one of these neighbors down here. In an NBMA network mode for OSPF, all neighbors are statically defined, and what will happen is unicast will be used to communicate with them instead of multicast. So we go to the routers, we'll say we want this one to be a designated router because there is an election in this network. We go into this router and we type in the IP address, we'll say 1.1.1.1, over here is neighbor 1. 2.2.2.2 is neighbor 2, 3.3.3.3 is neighbor 3, and so on. You statically type in each one of these neighbors. Now, there is an election, and the catch in this network type is that the DR must be fully connected to all of the other neighbors. And we're going to get more into these when we fully discuss running OSPF across an NBMA cloud. We're going to set these up left and right because this is one of the major challenges with OSPF. But the DR must have full connectivity to all of the neighbors. So would this guy classify as a DR or even a BDR? No way, because it can only connect to this hub. The same goes for any of these other neighbors. This one is the only one that could be the DR in this network, and it will maintain the database for this whole cloud. When this router sends an update in, this one will update it and figure out what that means to the topology table and send that update to all of the other neighbors. It is the central point of contact in this network. Point to multi-point mode is very similar to this, except number one, there is no DR election. Let me cut this out of there. There is no DR that's elected. And number two, the messages will be multicasted. So it takes the NBMA mode and adds the multicast capability to it. This is actually, I'll put a little star by it, Jeremy's favorite. I love that mode because it treats each one of these circuits as its own point-to-point connection. Even though it's configured on a multi-point interface, it looks at each circuit like a point-to-point connection. It's very similar to this one up here. Everything is dynamically taken care of. There's no DR, there's no BDR because we don't have DRs and BDR on a point-to-point circuit. And it all takes care of itself. This is one of the easiest modes to configure. However, that cloud needs to allow multicast and broadcast messages in order to support that point-to-multipoint mode. Regardless of what network you're communicating across, OSPF will build neighbor relationships with the routers that it's communicating with around it. Now, this is the process of how OSPF neighbors build and how they form those neighbor relationships. And before I even talk about the process, some of you may have seen something like this before, maybe back in the CCNP, but this is where it really gets important. Here's why. Here's why we're talking about this. On the CCIE lab, you're going to be working with OSPF, and you're going to have some weird situations that you're configuring. You're going to have OSPF neighbors that form, and some that form halfway, and some of them that end up in these strange states, and they're not exchanging data, and you're going to have to troubleshoot it. By knowing what each neighbor state means, you can figure out what point it's moved to in its neighbor relationship and begin troubleshooting from that point. Here, let's walk through this together, and I think you'll see it as we go. I have two routers here. I have Sneezy and Droopy, and they're going to be communicating across a broadcast network. Here's the way it works. This one's down, and let's say we just enabled OSPF, and it sends its first hello message. It happens to reach Droopy before Droopy sends another hello message back. So Droopy is the first one to know about the Sneezy router. It gets this hello message and says, okay, I know about the Sneezy router. It enters this state called init, initialization. So if I were to do a show IP OSPF neighbor on Droopy, I would see the Sneezy router and its router ID in the init state. Now Droopy will send a hello message right back out, and now Sneezy knows about it. And if I were to look at these two, they would both sit in the init state. They would list each other as a neighbor in the init state. Now, if any of those fields don't match in the hello packet, you remember we talked about the hello packet and I put those little green X's next to it? If any of those fields don't match, what's going to happen is they will stick in the init state. And just to hit those fields again, they're the area ID, the authentication information, the hello timer, and the dead timer. If those don't match, we are stuck in the init state. If they do match, and now all that is kosher between the two routers, they will enter what's known as a two-way state. And if you do a show IP OSPF neighbor, they will show two-way as the neighbor. And at that point, the DR and the BDR election begins. And that's where we elect the DR and the BDR based on the priority. And we'll get into that once we get into the configuration. But I want to take you right here. Let's say that there's a few more routers. Oh, let me get into my freehand draw mode. A few more routers on this network segment. We've got Sneezy, Droopy, and a couple other routers here. The neighbor relationships will form between all the routers and the DR and the BDR. So let's say this one is a DR, and this one is the BDR. Droopy and Sneezy will end up forming full relationships with those two routers. The relationship they maintain between each other, between Sneezy and Droopy, will be two-way. And I want to emphasize that point because I used to freak out. I would do a show IP OSPF neighbors on a broadcast segment. I would see some of them forming full relationships and some of them forming two-way relationships. And I'm thinking, oh no, something's wrong. Sneezy and Droopy aren't communicating. They have two-way relationships. Well, the reason why is because they will not form relationships between each other. They only form relationships between these two. When we see them in the two-way state, it means they've recognized each other, they see each other, and yes, their hello packets are understandable and all the fields match up, but they're not going to exchange information because they'll only exchange that between the king and the queen of the network. They remain in the two-way state. You may see this also when we get into the non-broadcast multi-access mode, where we have a DR-BDR election inside of that cloud. Some of the other routers may see each other, but they'll only be recognized as a two-way state. So let's pick up from here. The DR election begins. Once those are elected, we'll go through a kind of a little flurry of states after that, and you may or may not see them because it happens so quickly. You'll see this EX start state. In X start state, that means that we're exchanging those DBD packets, the database description packets, with the DR and the BDR, pretty much giving them the summary of our linked state database. They'll go through an exchange state right after that. And in the exchange state, they'll exchange the entire linked state database and they'll synchronize it. They'll get all the information. Remember, the DBD is just the summary of that database. It's the summary of what routes I have in my table. And during the exchange state, we're going to get all the detailed information about that summary. Once we go through those two states, we'll end up, and this kind of transitions right into loading, which is a brief flurry in between, and then the full state. Once we hit the full state, and this is where you'll see most of your neighbors, We have formed a full neighbor relationship, and we will not be sending any extraneous information other than hellos to make sure that they're still online, and just an LSA here and there in between to make sure that our database is still up to date, or anytime there's a change that takes place on the network, we'll send an LSA to let everybody know about that. However, full will be between DR and BDR in this case, and all the other routers and on that segment. Those are the neighbor states, and when we start doing the configuration, we do show IP OSPF neighbors and even doing debugs, we'll start seeing it transition between all of those states. Okay, I'm going to call this the OSPF mega concept slide because we're going to combine all of the OSPF area, router type, and LSA concepts into a single slide. And I feel comfortable doing this because you guys are at the CCIE level, and most of this should be review for you. However, when we get into the configuration, I want to make sure it's still fresh on your mind because we'll be using these terms, these area types, and these configurations all throughout the rest of the OSPF nuggets. So let's start off with the OSPF area types. And where does it always begin? Area 0. Always area 0, the backbone area. Some organizations are small enough that they'll never get outside of the backbone area. The backbone is the core of your OSPF network, and all other OSPF areas are required to directly connect to the backbone area. Now, there's the exception to the rule, and I know we're going to talk about virtual links, but let's not think about virtual links as of yet. That's one of the not so good practices, but can be done in the OSPF world. Now, outside of the backbone area, we might have some normal areas. And the reason that we create normal areas is to allow for route summarization. Unlike EIGRP, OSPF does not support route summarization everywhere, anywhere in the network on any interface whatsoever. It only is supported on these area boundaries. And we can get into the stub areas and totally stub areas and so on, but really people break it into multiple areas and just use normal areas just to support route summarization features. Now, this normal area has a router that's connected out to this external network. And actually, I don't even want to get to that yet because that's the router types. We'll talk about that in a second. Before we do, let's talk about the stub area. The stub area is the first specialized area type that we see, and what it does is it blocks route updates coming from any external network. So it will know about all the routes in area 0, it will know about all the routes in this normal area and all the routes over here, but it will never know about these routes in this RIP area because that's the function of a stub area. It blocks external route advertisements. A totally stubby area up here blocks external route advertisements and route advertisements from other areas. So it will only know about routes, and I keep nicking the whiteboard here, it will only know about routes in its own area. It will not know about routes from other areas or external routes. So how does a router inside of a totally stubby or even a stub area know how to get to this external network? Is it able to reach them? Well, yes, it is. Because whatever router is at the boundary of that stub or totally stubby area will generate a default route, a route of all zeros, saying anything that you don't know about, send to me, because this router is connected to the backbone, and so is this one. And they'll have the information that is able to reach outside of it. But these internal routers right here, they don't know about it. Their routing table is very small, and thus they are very efficient routers. And that leads me to my discussion of router types. Let's talk about the different red labels all over the screen, the different router types that are out there. First off, the easy one, I abbreviated these just so it's not so jumbled. I stands for internal. Internal routers are routers that really are inside of an area and aren't doing anything special. Now over here we have a B, and that is a backbone router. And by the way, some of these functions may bleed over. You can look at this as a backbone router, and the definition of a backbone router is just a router that has one or more interfaces connected to area 0. This is a backbone router, but it's also an internal router. We could put a little comma I here because it's internal to the backbone. Now, an area border router, or an ABR, is a router that has two interfaces connected to different areas. So we have one interface connected over here and one over here. Now it's not limited to that. We could have a third interface connected to another area and a fourth interface connected down here. But Two or more interfaces connected to multiple areas defines an area border router. And these are the ones that are able to tie multiple areas together, and one of the unique routers that are able to perform summarization. Now in this case, this router is an area border router slash backbone router because it's connected to area 0. It has one or more interfaces in there. Down here we have another router type, which is an ASBR. That stands for Autonomous System Boundary Router. This is a router that has one or more interfaces connected to an external network, which in this case is the RIP network. This is the other router that can perform summarization and now can perform redistribution. It can redistribute those RIP routes into the rest of the network. So those are the major router types that we can use inside of OSPF. And now let's talk about the LSA types. And we're going to kind of tie a bunch of concepts together as we talk about these. LSA type 1 is used as a normal routing update. For example, let's say that we had a few more routers in this area down here. I had internal connected to two routers right here. This internal router might send an update, an LSA update type 1, to its DR, and we'll say this is the DR. Now that DR will figure out what to do with that LSA type 1 and then send it out as an LSA type 2. So these are LSA type 1 and 2 are really just kind of normal updates. They're updates about areas and networks within those areas. So if this one went down, this router would send an LSA to its DR, and it would send it out to all other OSPF routers as an LSA type 2. LSA type 3 and 4 are different types of summary LSAs that are generated by the ABR. Okay? The area border router performs summarization. For instance, this might have all of the 10.x networks in this normal area right here. And this area border router, even though there's 10.1 and 10.2 and 10.3 and all the ones we don't see, can summarize this up as 10.x, and have just a /8 subnet mask on there. Now that is kind of an LSA type 3, but what most people don't catch, and they kind of understand LSA type 3s and 4s are summary LSAs, but ABRs generate nothing but type 3 and type 4. Even if we don't perform summarization in this area border router will send them into the backbone, all of these specific routes, 10.1, 10.2, as type 3 LSAs. The reason that they're generated as type 3 and type 4, and by the way, type 4 just describes the location of an ASBR. It's just the IP address of an ASBR, not specific routes. But the reason that they always send out type 3 and type 4 is because that is how, for instance, a totally stubby area knows how to filter them out. I mentioned that a totally stubby area blocks external routes and routes from other areas. Routes from this stub area and this backbone area. And the reason it does that is because in the RFC definition of a totally stubby area, it says totally stubby areas will not accept type 3, type 4, or even type 5 LSAs, because that's just how it's defined. So ABRs generate nothing but type 3, so by the time it gets here, based on the RFC definition of OSPF, it knows how to filter them. Now I mentioned type 5 LSAs. Type 5 are external routes. They're only generated by an autonomous system boundary router. When RIP starts sending routes and we start redistributing them into this normal area, they will come in as type 5. And the definition of a stub area says I will allow all of these first 4 types of LSAs, but I will block type 5 LSAs, thus blocking external routes. So that's kind of the technical definition of them. And that brings us down to the final type of LSA that we're going to talk about here, type 7 LSAs. These LSAs are generated by a not so stubby area, an NSSA. Now you might be thinking, well, wait a sec, you didn't talk about a not so stubby area on this screen. Nope, you're right. I saved it until now. Let's say that this router connected, you goofed up in your design, or maybe just your requirements demanded it. This router happened to be in Australia, and you acquired another company in Australia that was running RIP. So you have to have a router in Australia that links to it, but it's a stub area. How do we band-aid it in the meantime? Well, we create a not so stubby area. A not so stubby area is an area that is a stub that goofed up somehow and had an autonomous system boundary router installed inside of it, or the requirements demanded it. So now this RIP network, the company that we acquired in Australia, or whatever the situation is now redistributing external routes through the stub area. Well, that doesn't make sense. How does it do that? I mean, the definition of a stub area, by its very definition, says that it can't accept external routes. Well, through this band-aid method, what happens is this router, now an ASBR, takes these external routes and tags them as type 7 LSAs. What's a type 7 LSA? Nobody knows. It's a band-aid. It's a lie to this area so that this area will allow it to go through. All of the routers in this area have no idea what this LSA is. They're not going to see those routes. It's just a band-aid to allow them to get through the stub and out to the backbone, because the backbone can accept and understand those routes. When it reaches this ABR, the type 7 kind of, if you think of an encapsulation, think of it like this. We've got this route advertisement, and here's our external route. I'll put ER, external route. It's coming in as a type 5, right? Type 5 LSA, but we're bandaging it and putting a type 7 LSA header so it can make it through the stub area. When it reaches this ABR, what it does is go chop and chops that type 7 LSA header off the front of that router. So now when it gets into this area, it's a type 5 LSA again, and everybody knows and understands what a type 5 is. That's all a type 7 LSA is a bandage. Now, to even blow your mind one more, what if we connected this router to an external area, to some RIP or EIGRP network out here? Well, at that point, we would have a totally stubby, not so stubby area that does the same thing to get those type 7 LSAs into the backbone area. So, a lot of concepts, but that is pretty much all the areas, all of the router types, and all of the LSA types summed up into a single slide. That takes us to the end of this nugget, which has really been a vast technical overview of OSPF and all the key concepts. Now remember, we started this all off by talking about why OSPF rules the corporate world even though it was developed in 1987. It rules the corporate world because it is the first industry standard, that's the key, link state routing protocol that offers all the fast convergence features, classless routing, variable length subnet masking support that the corporate world needs. We talked about the OSPF communication network types, and then we delved into all of the different router types, areas, and LSAs on that previous slide where we just crammed all of that stuff in. Now, hopefully this has been a good conceptual review for you. If not, please come back to this as you get into the configuration nuggets of OSPF. If you're going through that and I start talking about, the not so stubby area and we're setting it up, you go, what was that all about? Please feel free to come back and just hop around through this nugget and reference those. I hope this nugget has been informative for you, and I'd like to thank you for viewing.